So, over the course of the next hour, I will show you projects such as how you can, by simply attaching a single camera to a piece of 3D printed plastic, turn that 3D printed plastic into a working game controller. I'll also show you some brand new work on how to help makers construct circuits and give them interactive debugging help for circuit boards. And I'm also going to show you some new augmented power tools that can give you real-time feedback on the types of tasks you're doing, basically downloading instructions into handheld power tools. But why, right? What's the purpose behind these tools, and who are we trying to help with these? So, as the title of the talk indicates, I'm interested in building design tools for the Maker Movement. So, maybe we should just start with a brief summary of what is the Maker Movement. Well, it's really this bottom-up effort to engage people from all ages and walks of life in learning how the world of products and electronics works and gaining hands-on skills to actively participate in shaping that work. So take this soldering workshop that was in Detroit. Here, there's really a variety of certainly different ages and different experience levels, all trying to be a more active participant in our material world. And of course, ground zero for all of this is the San Mateo Fairground. And Maker Faire is actually this weekend. It's starting today. So if you want to meet your 100,000 closest friends who are all interested in building and tinkering and experimenting, head to San Mateo this weekend. So this has grown from the very first year when I presented the work that Michael and I were working on to a crowd of, back then it was 20,000 people, to now there are well over 100,000 people who make it to San Mateo and more than 800,000 who make it to these events worldwide. Now, the Maker Movement is happening outside of academia, but also inside. And so hacker spaces or maker spaces are appearing in high schools, middle schools, and college campuses. So I want to show you a little bit about that as well. But maybe we'll start with just the question, what is it that people are making? What do we mean by Maker Movement? So you'll see many examples going from the whimsical. This is the banana synth. That plays music when you touch bananas, to artistic robots. This is Spinbot. This is a project from one of our lab managers at Berkeley, kind of a gentle and aesthetic introduction to the structures and also electronics behind robots, to the more technologically advanced. So this is super awesome Sylvia's watercolor bot, which is basically a CNC robot that happens to draw with watercolors instead of having some other industrial end effector at the end. And here's one of my favorite projects here. These are a bunch of teenagers who, together with their parents and various mentors, built a full flight simulator into a salvaged Cessna cockpit, and the flight simulator actually was mounted on gimbal axes with complete 360 barrel roll ability and hooked up to flight simulating software.
Their dad runs the algorithms department at Pixar, Tony DeRose. Very, very cool family.
Yes. So maybe we can see some similarities here. So from an engineering perspective, there tends to be this confluence of software, electronics, and also some mechanical engineering in many of these projects. And often they're not products per se, but really prototypes, custom one-offs, where making one is the end goal. All right, well, that's certainly nice for all those makers, but what's at stake for us as a larger community, as a nation? Why should we care about supporting the Maker Movement? And I'd argue there are at least three related reasons. There may be more. One is educational. So I'll let you read this quote from Alan Watts. Which just points to the fact that Our educational system is very good at equipping us with analytical skills, but maybe not so good at imparting the motivation for what we need those analytical skills for in the end. And so one of the promises of the maker movement in education is that it serves as a motivator and also as kind of a grounding application of STEM and STEAM skills. And just to, to admit, I have actually seen electrical engineers enter graduate school at UC Berkeley who are completely excellent mathematicians but don't know how to hold a soldering iron. And so this may be a counteracting force. Second argument is made by Eric von Hippel at MIT, which is that often innovations come from lead users rather than out of R&D departments at large corporations. And the maker movement and the associated tools can hopefully equip more lead users to act upon their insight in a particular domain. So think about Burton Snowboards, right? The biggest snowboarding company was created by snowboarders. And over time grew into a really big company. But it was really, the same is true for various medical device innovations. It's really the people on the ground involved in a sport or in a profession know what they need. And if you give them the tools to kind of scratch their own itch, then that can give rise to new companies and new economies. A third related argument is about knowledge about manufacturing in the United States. So Denning wrote an article, Why Amazon Can't Make a Kindle in the US Anymore, which argued that the decades of outsourcing have actually led to all of the important know-how in manufacturing to also move along with it. So it is much easier these days to take your idea to Shenzhen and learn about the local supplier ecosystem there than try to do the product in the US. Now, how can the maker movement change that? Here's just one example. This is Type A, a local 3D printing company, and they built their first 100 or so products basically at Tech Shop or other fab labs here in the area out of laser cut plywood and hardware store hardware. And that allowed them to gain enough expertise and capital to then now manufacture something that looks much more polished. And can be mass manufactured. So the White House has taken note. Starting in 2014, there was a White House Maker Fair. Coming up in June, there's another National Maker Fair in Washington, D.C. So this is, I think, for some of the reasons I just outlined, starting to be a national priority to support these efforts because of education, innovation, and just manufacturing knowledge. Now, another question you might ask is, does the maker movement need research? Do they need the help of HCI, computer scientists, mechanical engineers, or are they just fine? Well, I would, of course, argue that there is interesting research to be done and to be contributed here for a number of reasons. First, what you see in the maker movement really inverts how our traditional model of how we think about engineering education. So the traditional engineering education is, welcome to college, take some math, take some physics, maybe some chemistry, then we'll teach you about signals and systems, then an assembly, then come programming languages, operating systems, and all the way at the end, you get to do a nice project that puts it all together. This is turning it upside down. People are motivated to build some project, and then the first iteration gets 80% there, and then something doesn't work. And so that generates a pull, a desire for new knowledge, but it has to be context-specific and just in time. The second interesting part here is that these projects really combine design process, so the exploration of what one should build and the specification, what it should be, with fabrication, the actual realization of software, electronics, and hardware components in one iterative cycle. Third, we're seeing just a new digital fabrication tool set making its way from industrial production into end user use, and that brings a whole set of questions with it, namely that amateurs just need different abstractions and affordances from either complete novices who are maybe in an educational program to become experts, or existing experts who have a degree in a specialty. So I think all of these imply a need for new appropriate design tools. So what structures really most or all of the research I'm going to show you today is this research theme for me to try to understand what the 21st century workshop looks like. And let me give you just two examples of really inspirational prior workshops that many of you have probably are familiar with, but I just want to bring to mind. The Wright Brothers workshop, right? Inventing the first maneuverable, controllable flight happened in a workshop that was really informed by their work as bicycle mechanics. So it's manual power tools that you see here. And of course, just down the street here, Hewlett and Packard's garage that allowed them to build their first instrumentation amplifiers and the whole world of information appliances that grew out of that. And so what should be in the garage, the workshop of the 21st century? Well, I see three core components. The first is sophisticated design software that allows users to specify the intent at a functional level of what it is they want to create. That connects to digital fabrication tools that then automate some, but not all, of the production task, taking files from design software as input. And finally, ubiquitous electronics that are really suffused in all of these products that can be as easily programmed as web applications can be today, but that interact with the physical world. Also, files, drills, saws, etc. They're not yet obsolete, but we understand what we need to teach people how to use them. Okay, so design software, of course, enables users to create detailed plans and code how their creation should look like and work like. And this is really where a lot of our work as computer scientists comes in. I and my students and collaborators create the software that lets users create the models and plans. Now, something else that I'm not working on, but which enables this transformation that we see to occur is, everyone knows Moore's law. Well, I think there's a second law at work that is slower, but maybe as impactful, and that is the scaling down of industrial manufacturing equipment to the point where it becomes feasible to have one in your lab, at a local store, and perhaps for some of those machines also in the home. Now, granted, desktop fabrication it's not nearly as powerful as $1 million CNC equipment, but the key is that it'll be used by many more users for many more tasks than the industrial machines. And finally, ubiquitously programmable hardware. Moore's law at work, not about scaling up in terms of capability and power, but scaling down in terms of being incredibly cheap, running complete operating systems, et cetera, on a couple of cents of silicon, and also being small enough and energy efficient enough that you can now integrate programmability into any device, whether battery-powered, energy harvesting, or connected to AC power. All right, so I've been, with my collaborators, trying to build and prototype this 21st century workshop at the Jacobs Institute for Design Innovation. There's a brand new building on Berkeley's campus. We sit geographically and maybe also in spirit right between computer science and mechanical engineering. We opened in August 2015, so we've just finished our first academic year. This is roughly what the building looks like. So we have a number of studios. Two of those studios are never assigned for classes. They're always available for drop-in tinkering and building. But then we also hold design classes either at the scale of 50 or 100 students. And then kind of sprinkled throughout the entire building is digital fabrication equipment, multi-material and elastomer printers, laser cutting, circuit board milling, kind of the whole range of what you here have in room 36. And at the, is that right? And at the PRL. Here, just a couple of quick impressions of the inside of the building. This is our first floor open maker space, and this is what a classroom would look like.
Is it open 24 hours a day?
It is not open 24 hours a day. We open at 8:30 a.m. and we close at 11 p.m. During the day. talking with our professional machine shop staff, they say, rarely do good things happen after midnight in a machine shop. So in our first 2 semesters, we've had about 15 different departments represented. I can't believe it, but 50 different courses took place and about an enrollment of 3,000 students. So Berkeley is big at the undergrad level, and we kind of went from 0 to 3,000 very, very quickly. Let me just highlight 3 concrete projects here, or 4, let's see. Here's a type of project that came out of mechanical engineering. This is Daniel Lim and collaborators working with a local girl who was born with a deformity on one of her hands, trying to take prosthetics from something to be hidden to something that she had a role in co-creating and is proud of and wants to show off. So her superhero hand, and this was done together with the Enable community, kind of an open source community of low-cost prosthetics. We just had our drought restrictions lifted, but don't get too excited yet. Who knows what happens in the next couple of years. This was a class project in my interactive device design class of a water-powered fixture-level water flow monitor. So a mechanical engineering student designed this 3D printed impeller that has magnets on the outside. When water rushes through, that spins. It induces a current in a copper spool that's on the outside, and that produces enough current to power up a microcontroller that has some Hall effect sensors that will measure the flow rate and then has a low energy radio to send those monitored levels to an application where it can then be tracked and forwarded, et cetera. And this is actually, this is now a nice Berkeley-Stanford collaboration in that we came up with the first iteration of this design in class, and then afterwards Phil Levis and some students took on that design, did another design iteration, and I believe it's now deployed in a Stanford dorm measuring water consumption. Here's a more whimsical example. This is a rocking chair that generates energy to charge your phone while rocking, and I like it because it just shows the interconnectedness of different skills, right? So someone had to learn to weld to put together a frame that could withstand the weight. Someone got really into woodworking to do those compound angles of the back. And then the students found an expert in energy harvesting to just think through, well, what's the right mechanism to extract as much energy as possible out of that rocking motion? Turned out it was a suspended pendulum underneath the chair. And so they then did the circuits for that, and there's also an e-paper display integrated into the armrest. And one last one, just to hint on that there are tremendous applications in the medical domain. This is a project that where the idea came from our collaborators at UCSF, where people with sensory ataxia lose feeling in their feet. And that means, if you think of it from a controls perspective, you're starting to walk open loop. You lack feedback, and that leads to falls, which leads to injury and further complication. And so the idea here is fairly simple. Pressure sensors in the soles of the shoes that then wirelessly transmit the footfall signal to your back, where you have cell phone vibration motors applied to your back to nerve endings that still work. And it's quite amazing seeing some demo videos how within 15 minutes of having this device, people rewire and can interpret that signal and become more sure in their gait. So once again, you see this connection of there's some mechanical parts, there are custom electronics, and then quite a bit of software as well. All right. So that's just the first part of the talk, what's happening in the Maker movement in general and what's happening at Berkeley in particular. So now let me connect this to particular research projects in my group on building new design tools for these domains. And just in case we run out of time at the end, let me just make sure I state this explicitly that, of course, the majority of this work was done by a fantastically talented set of students and actually some collaborators here at Stanford as well. So I want to give you just a brief glimpse into 3 different research areas related to the Maker movement that we're pursuing at the moment. The first one is prototyping tools for interactive devices. How can we make it more rapid to explore the space of interactive devices? The second one is on learning and debugging tools. And the third area is on hybrid fabrication. So what lies in between the tools you pick up at Home Depot today and a fully automatic 3D printer? So we'll just do these one by one. So guiding question for this first area is, how can we make hardware prototyping as fluid as prototyping graphical user interfaces? Well, we've now had decades of really good tools that make it very quick to design screens and link them together through interaction events. Well, first, why might we care about hardware prototyping of interactive devices? I'd argue that there are performance and virtuosity benefits from tangible interfaces that just hitting your fingers on a flat sheet of glass cannot replicate. So if you ask really invested gamers, they will go into exquisite detail about the haptics and the feeling and the capabilities of their game controllers. Similarly, DJs to this day prefer the physical tangibility of playing with vinyl records and turntables over just playing software on your laptop. And you see this in interfaces for flights, for airplanes and flight simulators, etc. So there's a whole space of why creating tangible devices still matters in this day and age. So how are they created today? Well, if you look into what industrial design labs publish, such as Microsoft Hardware, you see 3D printing is used ubiquitously to create looks-like and prototypes. So they give you a sense of the aesthetics and the ergonomics, but they're just pieces of plastic, right? If you actually want to turn this into a working game controller, well then a kind of very detailed and complex process of electromechanical co-design has to occur. You do the circuit board, then you have to fit the circuit board in a control, you have to make sure that all the buttons and joysticks are exactly at the right place, and really, when you're doing that, you're in complex CAD, which is kind of at odds with the goal of prototyping, where you want to rapidly explore the space and not already commit to all of these design details that you're really not yet sure about. So, our first stab at this question, how can we make hardware prototyping more fluid, took motivation from tangible modeling. So we ran a user study where we asked our participants to sculpt various augmentations for their devices, like a bike holder for your cell phone. And what we learned from that is some things are really easy to express using sculpting, and while other things push the boundary of your knowledge of sculpting and are really much easier expressed as annotations, such as put a joint here, or this is where the complex mechanism goes. And so combining sculpting and kind of high-level semantic annotation, we took that as inspiration for a project called Maker's Marks, where the vision was the following. If we give you some sculpting materials and a set of stickers to annotate the function, the intended function of your object, that should let you easily create things such as this mocked-up game controller, where you sculpt the shape and then you put stickers on wherever you want particular I/O affordances to fall. And if we then give you equivalent electronic parts, wouldn't it be nice if we could automatically then, from that, generate the right kind of detailed design to fit all of these pieces into your sculpted geometry and give you a working controller? So the idea here is we start by sculpting the geometry, placing those annotation stickers, and then we 3D scan your object and the annotations. And we use a 3D scanner that creates both geometry as well as texture images. We then take those texture images and run computer vision algorithms over those images to locate the points where you place those stickers. So that lets us locate those stickers in the 2D images, and because we know how the textures are applied to the 3D model, we can project that back into 3D space of the scanned model. We can then say, oh, you placed a joystick sticker on the model, so we can now replace that by a digital model of the physical part and check whether you could actually place that part at that point on the controller, and then automatically generate mounting geometry so that when we print it, you can snap that equivalent part right into your 3D print. So this is, for example, what a processed model would look like. So we generate cutouts where parts protrude through your model. We generate fasteners and mounting bosses, and we also shell the entire model so it's hollow on the inside and generate suitable lips to put the pieces back together. So in order for that to work, we need to create these models for physical parts, right? So we need the rough geometry, we need the clearance, kind of how much space it needs to move around, and we also need a definition of how you would mount that geometry in a shell. Once we've processed the model, we then 3D print, and then afterwards the user just takes these off-the-shelf electronic parts, snaps them in, and ends up with a working device. So we're not talking about the software here, right? The interaction still needs to be defined, but at least there are already reasonable tools for that step. So the key idea here is that our maker expresses the shape intent through sculpting and the functionality, the interactive intent, through this placement of marks. And the tool then automatically handles the detailed geometry modification. Now, the main hurdle here might be, you might think, is that we actually need these 3D models for all of our electronic components. Otherwise, we can't do the automatic processing, right? Well, but it turns out, if you look around, vendors for mechanical parts already give you all these CAD models. So if you go on McMaster, which is the predominant source for parts for mechanical engineers, the vast majority of parts they sell already come with CAD models in various forms. So we actually don't think that is too big of a hurdle in practice. Yes, it has to be done for each component once, but vendors actually have a financial interest into generating these models. All right. So the first step at this problem was to make it easy to snap in pre-existing PCBs that someone already created in kind of a plug-and-play electronics toolkit. So our second question was, well, it seems that 3D printing will likely in the near future have the ability to print conductive materials as well. So can't we just print all of that connectivity into the model right as we print the model and then just add all of these components, individual components in the end? So here was kind of that vision that maybe we can create these interactive objects like this touch-sensitive Stanford bunny by just printing the whole object and inserting some LEDs at the end. And so the idea is that actually inside of the model, you basically do 3D circuit board routing and connect all the different input-output points automatically. So we built this is a little washed out, a lot washed out. We built a design tool that basically allows you to create these 3D conductive routes through the insides of objects by only specifying very high-level intent, like route something from this point on the surface to this other point of the surface. And we then figure out appropriate routes that don't intersect, that don't exit the geometry and that don't intersect other paths. Now, the vision here is that you can print this all in one go. The reality is that we didn't have such a machine available at the time. So we resorted to a manual process, which is you print all of this, you dissolve the support material inside of the pipes, and then you just fill it with conductive epoxy or conductive paint. And that led us to generate a bunch of different working models such as this. So we're working with some neuroscientists who are very interested in different models of brains of different species. So we could generate this interactive brain and other interactive objects. And also we have a different algorithm for basically controlling the shape of the path inside an object so you can create these neon art objects. Now, we weren't looking too far into the future because we knew this technology was coming down the pipes. And so now in our lab, just over the last couple of months, we've had one of the very first voxel 8 printers, which actually has a syringe in addition to an extruder that can deposit this conductive material right through the middle of the print. So that manual process will go away. And we're really lucky also to work with Autodesk on this project. And you can actually find this pipe tool right now for 3D circuit board routing in Autodesk's Mesh Mixer, which is a free kind of mesh modification tool. All right. Now let me take a third run at the same problem, just to maybe also show you our thought process in the lab of not thinking, you know, there's only one solution to a problem, but really exploring a space of alternate solutions. What if we didn't have to put any PCB inside? What if we could take a piece of plastic and transform it from a passive piece of plastic into an interactive device by only adding one extra ingredient? Kind of think of a super sensor that could just detect everything a user does with that game controller. So this is the clip you already saw at the very beginning of the talk. Our super sensor is a camera. So we take a camera, we integrate it into a 3D printed device, and then we do computer vision on the inside of that device and interpret the movements of the users pushing buttons or moving a joystick turn those into interaction events and let you control games and other applications with it. All right, so how does this work? So Sauron is an add-on to just a commercial CAD package. We use SolidWorks in this case, but there's nothing particular about choosing SolidWorks. So you have your 3D model of the device you're building, and then you add a virtual camera into that model. And our virtual camera has the right dimensions, but it also has the camera parameters, like the field of view. So you take our virtual camera and you mate it with your controller. And you can already see what that lets us do is we can now run a simulation. What of all the different input components on this device are actually visible by the camera? So things in green, we can just track with computer vision right away. Now, unfortunately, there are also these other components in red that are not visible to the camera. So what do we do about those? So this is where, the naive solution doesn't work, so you got to be a little more clever algorithmically. And our key lever here is that we haven't printed this yet. This is just a digital model, right? So we can modify the shape and the geometry of that model to make the computer vision task easier. So camera here is in green, the field of view in light blue. We have a button here that is not currently visible, but we can take the end of that button and just extrude it until it falls within the field of view of the camera. So let me make that a little bit more concrete. Here is a model of a fairly complex object with buttons on all possible sides. We can just run this extrusion check over it and then extrude all of the buttons to a varying degree till they all fall into the field of view of the camera. Now that works sometimes, not always. Consider this button here. If we just extrude it straight down, it never meets the field of view. But here comes just elementary graphics into account. We can start raycasting rays from the camera into the scene and bounce it off the boundary, the shell of the object. So we take these rays, bounce them off the surface normal of our shell, and then we look at rays that hit the component we want to track. What do we do with these rays? Well, wherever those rays hit the boundary of the object, if that surface were to be specular, right, then rays would also reflect from the object back from that point into the camera. And so what do? Well, we tell the maker to glue craft mirrors into those locations on the inside of the object. So kind of a theme that appears here is use automation whenever possible, but don't discount the possibility of being able to go quite a bit further if there's just a little bit of manual labor involved as well. So injecting conductive ink or gluing mirrors in the right spot at the right time. So then you print the device. If you have a single color printer, then here's the highly technical step of highlighting the ends with a Sharpie marker. We've also printed on multicolor printers, so you can have these marks that are easier to track by the camera. You can automatically print them in a different color. Right now, the trade-off of that is, that's about an order of magnitude more expensive to print in multiple colors than in a single color. All right, so then we have the model, and we add the camera. The camera comes with its own ring lights to illuminate the inside of the object. And then the vision tracking is done through interactive calibration. So our CAD model will highlight a component, say the slider, and we say, please move it through its range of movement. And as you do that, we can, in real time, build up a model of, in this case, blob tracking, from minimum to maximum position. Now you might ask, why do we actually have to do this calibration? We have the model of the camera, and we have the model of the geometry. We should just be able to infer all of that. And that just comes down to the limits of the precision to which you can actually, manually screw that camera in, and if the lens is perfectly centered. So it's safer to have calibration than to just infer, the right answer. So for some components, we do blob tracking. For others, like the scroll wheel and the trackball, we do optical flow. So these are really just off-the-shelf computer vision algorithms that work perfectly adequately here. So in addition to these game controllers, we've also built various mice and something that's near and dear to my heart as a former musician and DJ is DJ controllers. Now just a quick word on evaluation here. We kind of proceeded in two different directions to get some triangulation of how of the limits of this technique. So on the one hand, we had a lab study where we brought in mechanical engineering students, so students who already knew SolidWorks, said, here's how this technique works. Please design us a DJ mixer that leverages capability. And they were all able to do that within the span of 2 hours or so. And they were actually quite clever in putting the camera in different unobtrusive locations and manually working with this technique of placing mirrors. So for example, you can have the camera in the top so it bounces off the bottom and reimages the top so you have a little wider field of view. Now, what we also did is we then went to GrabCAD and just downloaded a whole bunch of models that were tagged with interactive device, and we did the analysis of loading up that model, positioning our camera. Could we, with our techniques, sense all of the inputs and outputs? And so things that are DJ mixer sized, yes. Game controllers, 8 out of 10, yes. But there were some where it was not possible. And so wherever you have inputs that are kind of satellite to the main core of the device and only connected through a thin channel, a single bounce will not make those visible. So you could extend that technique to go to multiple bounces, but it's just the caveat here is this will not work on any arbitrary model. But I think for prototyping, actually, while the designer is still in the loop, right, that can also be a conversation of, can I easily modify my model to make this sensing technique work? All right, so key ideas for this part. Use vision sensing as a super sensor on the inside of fabricated objects. And then there's this co-design of the geometry and the sensing technique. So we can modify the shape to create an easier computer vision model, which is the flip side of what computer vision research usually does, right? Which is pointing the camera onto an arbitrary scene out in the world and trying to understand that scene. And we're saying, no, we actually control the environment that you're looking at, so how can we make that environment better so that existing algorithms will perform better? You cannot just do this with vision, so very quickly let me tell you, here's the same conceptual approach, but a different sensing modality. So instead of using your camera as a super sensor, you can also use a microphone as a super sensor. So our idea here is we'll 3D print input components with a time mechanism so that some sound is created, some vibration is created whenever a user provides input. So take this button, there's a plunger, and then we 3D print this tine. So as you press down, that tine gets deflected. Eventually it'll slip, and then will vibrate back and forth. And so if we now put a contact microphone on that 3D printed piece of plastic, we can pick up that vibration. And the basic intuition here is that tines of different length will vibrate at different characteristic frequencies. And so if we generate tines of different length, we should be able to distinguish different inputs. So you can not only do this with buttons, you can do that, for example, with sliders as well. And so what are the different variables that determine the characteristic vibrational frequency of a tine? Well, it's breadth, thickness, and length. And this is basically vibration of a cantilevered beam, right? So there's a closed form solution, which is the fundamental frequency depends on material properties, so density and Young's modulus, and on geometry of the tine. But the nice thing here is we have this closed form solution. We don't need to train our system. There's no machine learning involved here. There's just some simple signal processing, and we already know what kind of frequencies we're looking for. So what we do is we run real-time windowing over the incoming sound, do the FFT to look at the spectrogram, and then what you find whenever a tine is struck, there's this transient region where there's just activation across the spectrum. It's a big noise right when the tine slips. But shortly afterwards, there's the steady state, and in the steady state, one single frequency clearly comes to the fore. So that is our F0. And so the algorithm is very simple. It's do an onset detector till you see a whole bunch of energy, then wait X milliseconds till the transient is over, and then look for the dominant frequency afterwards. Here's just some technical evaluation. So we tend to do very well in the 1,000 to 2,000 hertz range, and then it gets dramatically worse afterwards. And that has to do with the fact that as your tines get shorter, the energy and the time for which they vibrate becomes increasingly shorter. And so that window after the transient to look for the characteristic sound becomes shorter and shorter, becomes harder to find. All right, so that was a quick overview of prototyping tools for interactive devices. That's mostly work that's already been published in the last 2 or 3 years. I'm now going to get to the experimental part of this talk, where I'll just show you some unpublished work that's really hot off the presses and hasn't been really, I've shown it once before. So the second time you ever see this. So work in progress, caveat emptor. So first, I'm going to tell you about work we're doing in tools for debugging electronic circuits. So who in the room has breadboarded circuits on one of these breadboards before? Almost everyone. Yeah. So at Berkeley, if you're any kind of computer science major, you will take 2 intro EE classes and build circuits of one of these. And just to be clear, so you build circuits on these. The connectivity looks like that if you haven't seen a breadboard before. So everything that's plugged into a row is connected, and then the power buses are also connected up and down. Now, breadboards arose in the 70s as an answer to the question of how can we rapidly plug together different discrete components to get a working circuit. So they're fantastically successful in that they've become synonymous with prototyping electronics. But they have a couple of issues, right? So if you build anything of any complexity, it becomes very hard to understand whether what you've built is actually what you wanted to build. So there can be loose wires, there can be power issues, often there might be questions of component polarity. Have I plugged my LED or a capacitor in the right way? You can just wire things incorrectly to the wrong row or pin, and sometimes components can also break. That tends to be the first student hypothesis. It's not usually the most likely hypothesis, but yes, broken components exist as well. So what's the approach for debugging these circuits? Well, it's point-wise measurements, right? You make a single hypothesis of what's wrong, and then you break out the multimeter and measure at the point in the circuit that corresponds to that hypothesis. And you can do that with a multimeter or with an oscilloscope. Now, our research idea here is that point measurements require you to already have a hypothesis about what the problem is with the circuits. We know from studies of programmers that non-experts are not all that accurate at generating reasonable hypotheses the first time around. So how about we replace point measurements with ubiquitous instrumentation? That means measure everything all the time, and based on those measurements, foreground likely problems with the circuit. And if you then also have some model of what the circuit is that someone is trying to build, right, then you can relate the real-world measurements you just obtained on the breadboard with the model of the circuit and how it should be working. So here is our toast board, the augmented breadboard. There are, on the board itself, there are LED bars that show you voltages at every row, kind of in situ. But then we also have a software client that highlights those voltages. And in that software client, you can then also create a model. Here's the schematic of what my circuit is. And we can then use that model to automatically debug your circuit. So for example, here, various warning signs show up. This LED may be inserted backwards or broken. How do I know? The voltage drop across these rows is not what I would expect. And so you reverse the LED, and we update the measurements. The warnings go away. All right. The idea here behind that board is we take a regular breadboard, and then we connect it to a multiplexer scan chain where we row scan every single row of the breadboard continuously. Then we have another small microcontroller underneath the breadboard where we just take all those measurements and forward them to software. And in the software, then we can have the model of the circuit. So here's the PCB we manufactured for that. You take a regular breadboard, you peel away the foam backing on the back, and you just adhere it with conductive Z-axis transfer tape to this PCB that has exposed conductive rows. And then we just have this multiplexer cascade, which basically, with one analog pin, allows you to scan through all the different rows on the breadboard. And as I mentioned, so we have both onboard feedback. That lets you determine simple errors like these two rows are lit up. I thought I was connecting that wire to the resistor. There should only be one row lit up. And then in software, you can get more complex debugging based on expected behavior of the circuit. So we just got this working 3 or 4 weeks ago and are looking to deploy it in classes this fall. All right, in the remaining 3 minutes, I'll just quickly touch upon some other ongoing work on hybrid fabrication tools. So we're really interested in the space of semi-automatic fabrication. So think about the degree of automation and intelligence that you find in products. A hammer has no automation and no intelligence. It's all in the wielder. On the other hand, a 3D printer is completely automated, right? You just download instructions, and other than some manual setup and cleaning afterwards, the rest is automated. You can add a motor, and you end up with some degree of automation, but still no intelligence. So what's in this space in between? We have two projects ongoing in the group right now, one on augmented power tools and one on CNC decoration. So with augmented power tools here, the key idea is let's augment common tools with state sensing, displayed feedback, and network connectivity. And then show continuous feedback based on those sensing for skill training. So how do I become a more proficient user of the tool? And use the network connectivity to allow you to download more complex programs, sequences of operations that you want to accomplish, not only on one tool, but maybe on a whole ecology of augmented tools. So our augmented drill has basically cell phone distance sensors in the front that gives you a distance and also an angle to the plane of your work material, some computation, and then a laser projector for feedback. So what does that let you do? Well, you can, for example, drill a blind hole to a target depth of exactly 12 millimeters. And on the side, a little harder to see, there's also orientation feedback that shows you whether you're actually perpendicular. Perpendicular is maybe the easier case, but sometimes you have to, let's say, drill at a 45-degree angle, and estimating that freehand is quite difficult. Now, many operations actually in woodworking and carpentry are really operations that sequence multiple tools together. So you drill, you cut something, then you drill, and then you join multiple parts. And so we have a complete description language for these types of operations that can be parameterized. So a user can, or a creator of plans can, create these and give the user freedom of how to instantiate these plans. So in addition to the drill, you can imagine augmenting all kinds of other tools. So for example, here's an augmented saw that has descent measurement, so how steady are you cutting, which impact surface finish, and then also has distance measurement, so digital readouts are quite common on many machines. But this distance measurement can be tied to the goal of what you're trying to cut, right? We can load the instructions into the saw and give you feedback based on that. So here's just a quick clip of that in action. It basically gives you feedback. No, stop. You overshot. And so we're working through a range of different building projects right now and studying how end users benefit from these tools. So let me show you one more. We've become interested in emerging hybrid practices that really merge manual work with CNC automated machining. So they're beautiful, antique vases that have now modern 3D printed parts, or various surface decorations. And so we focused on the problem of CNC surface decoration. So here, the key idea is, well, 3D printers are great if you want to create something entirely from scratch. But what if you enable makers to modify existing objects? So objects they already care about, they have some emotional attachment, or they're made out of materials that you can't yet 3D print. So our first foray into this area is digital surface ornamentation. We're going to once again reuse 3D scanning as a core step, and then so we're going to 3D scan some existing object and then allow you to modify it using various digital authoring methods. And then leave the execution to a CNC machine. So the idea is, right, we scan some existing object, like this manually created sculpture. And then for this project, we actually created our own machines. So these machines don't exist yet, but it's almost trivial to convert a consumer-grade 3D printer into a decoration machine. Basically, what you do is you replace one linear axis with a rotational axis, and then you add an engraver bit holder or a pen holder. This can also work with other machines. This is an off-the-shelf router that can also do the same job. So the idea is we scan your object, and then that object may be really complex, right? But we have a 3D model of it, so we can, from that 3D model, automatically generate mounting geometry that will hold an object of an arbitrary size and shape securely in the decoration machine. So we 3D print these custom mounts. And then, sorry, we seem to have lost the key part.
Banksy bot, artists begin by 3D scanning it. They can choose to author a design in one of three ways.
We're scanning the object.
They can virtually decorate.
And then you can author your augmentation. You can either just paint on an object. This is fairly straightforward.
And also import vector graphics to map onto the object's surface. As in other design software.
But in addition to painting, there's also we experiment with live engraving. So you paint in real time, and basically with like a 5-second delay or so, we start engraving on an actual object. And that allows you to really bridge that gap between the virtual representation and the actual physical object. Or, because we have a 3D model, we can also print it out at a different scale, right? So you can scan something, we can print it out larger, you draw on it, and then we just scan it back in, extract those annotations, and then generate tool paths to engrave. Okay. So to sum up here, how do these tools that I presented help makers? Well, key themes from the user's perspective, they allow you to describe your goal at a higher level of abstraction. This is what computer science does really well, right? Elevate the level of abstraction that you're operating on. Let the tool take care of the mapping of the high-level goals into low-level operations. But there's also this tension between whether what you create is a black box abstraction or a glass box abstraction. So when complexity is inherent in a task, like understanding what that circuit is in front of you, then you don't just want to jump to a higher level of abstraction, but you want to help people understand by making the invisible visible. So add instrumentation and sensing and visualize that extra data that is not readily perceptible by the user. I think for a number of years, there'll be great leverage by intelligently combining utility out of digital fabrication, things you can do automatically, with carefully chosen points at which manual labor will still push the envelope of what you can build. And then there's this idea of receiving guidance through context-specific interactive examples and tutorial formats. Just to sum up the key technical themes here, integrated approach to mechanical, electrical, and software aspects of the project, right? Because so many of these maker projects really unite the three. So you have to think of all three simultaneously. That's not just complexity, it also makes some problems easier, like modifying geometry to aid sensing. Then, given a high-level specification, co-design geometry and sensing approaches together, right? Combine computer vision, artificial intelligence, digital signal processing with geometrical design techniques. Then there's the topic of ubiquitous sensing, right? Work with rich real-world data wherever possible. So this includes scanning and also scanning of 3D models and also of electrical circuits. And then in general, integrate 3D scanning as a useful tool, which we haven't seen a lot of in the Maker movement, but abstract away from having to deal with hundreds and thousands of polygons. All right. So where's this going in the future? In our lab right now, what we're really excited about is actually advances in material science that start to impact the Maker movement, such as multi-material printing, printing a flexible elastomer object. And so we have some of those prototype printers, By the time they trickle down to the Maker Movement, it will be a couple of years, but we want to have those techniques ready now when they do. I also think that physical construction debugging tasks are ideally suited to augmented reality, especially if you can sense things about the circuit, things about the object. It does not necessarily mean strapping a big display to your head, right? The augmented power tools are another way of thinking about augmented reality, or the breadboard, where you show the right information in context, just not overlaid using a head-mounted display. And in general, we're really interested in using Jacobs Hall as this living lab to deploy and test these tools. So, thank you.
Maybe a couple questions. Yes.
Yeah, I had a question about the breadboard that you're looking at. So it looks like the error detection that you're doing is kind of analogous to throwing a runtime error in software. So I'm wondering, like, to what extent do you think you can borrow from ideas in software debugging, like printing out a stack trace or something, and to what extent is it like necessarily going to be different for hardware?
Right. So excellent question, and yes, these techniques are very much inspired by the kind of affordances we already have in modern IDEs, right? Like constant compilation, giving you red squiggly lines. And so very much inspired by that. And actually, the next step for this project will take it a lot closer to software development as well, because what I show you is only about purely analog circuits, right? What most people are building right now are circuits hooked up to computation, to microcontrollers. And so the very next step that we're already working on is pushing this boundary to analyze software and circuit behavior together. And there, the software debugging techniques will become ever more relevant. Yes?
One of the goals you mentioned at the beginning was to use these tools to help gain expertise in actual manufacturing techniques, like in China. But there still seems like there's a big gap between this realm of tools and like what a Shenzhen factory would actually have. So how do you see that gap closing over time?
Yeah, absolutely. So just to set the context again, I think the Maker movement in general has the promise of bringing more people into the design of physical products, which will then lead them to gain manufacturing expertise if they want to bring those products to market. The prototyping tools I've shown you there's definitely a gap, because there the goal during prototyping is actually not having to worry about all of those manufacturing details. So abstracting away from all of those problems so you can get to the question of, well, is this even the right design earlier? Now, there's a separate set of projects that you can think about that are about bridging the goal to manufacturing. Some of those are technical, and some of those are social in nature. So, for example, we've had a project in the past that is really around connecting makers to people with manufacturing expertise, which right now in the US tend to be retired machinists, right? So how do you create the right social, community to enable people who are quite likely remote with the right expertise to give you input on a particular design you're working on. The other part is the work that my colleagues have been doing is, for example, capturing information about different manufacturing processes and giving you basically expert systems that say, I want to make the following, and out comes the recommendation, you should really use injection molding for that.
All right. I think Bjoern will answer a few more questions maybe in person here. Let's thank him one more time.
Yeah. Who are all interested in building and tinkering and experimenting, head to San Mateo this weekend. So this has grown from the very first year when I presented the work that Michael and I were working on to a crowd of, back then it was 20,000 people, to now there are well over 100,000 people who make it to San Mateo, and more than 800,000 who make it to these events worldwide. Now, the maker movement is happening outside of academia, but also inside. And so hacker spaces or maker spaces are appearing in high schools, middle schools, and college campuses. So I want to show you a little bit about that as well. But maybe we'll start with just the question, what is it that people are making? What do we mean by maker movement? So you'll see many examples going from the whimsical. This is the banana synth that plays music when you touch bananas, to artistic robots. This is Spinbot. This is a project from one of our lab managers at Berkeley. Kind of a gentle and aesthetic introduction to the structures and also electronics behind robots, to the more technologically advanced. So this is super awesome Sylvia's watercolor bot, which is basically a CNC robot that happens to draw with watercolors instead of having some other industrial end effector at the end. And here's one of my favorite projects here. These are a bunch of teenagers who, together with their parents and various mentors, built a full flight simulator into a salvaged Cessna cockpit. And the flight simulator actually was mounted on gimbal axes with complete 360 barrel roll ability and hooked up to flight simulating software. And the maker movement and the associated tools can hopefully equip more lead users to act upon their insight in a particular domain. So think about Burton Snowboards, right? The biggest snowboarding company was created by snowboarders. And over time grew into a really big company. But it was really, the same is true for various medical device innovations. It's really the people on the ground involved in a sport or in a profession know what they need. And if you give them the tools to kind of scratch their own itch, then that can give rise to new companies and new economies. A third related argument is about knowledge about manufacturing in the United States. So Denning wrote an article, Why Amazon Can't Make a Kindle in the US Anymore, which argued that the decades of outsourcing have actually led to all of the important know-how in manufacturing to also move along with it. So it is much easier these days to take your idea to Shenzhen and learn about the local supplier ecosystem there than try to do the product in the US. Now, how can the maker movement change that? Here's just one example. This is Type A, a local 3D printing company, and they built their first 100 or so products basically at Tech Shop or other fab labs here in the area out of laser cut plywood and hardware store hardware. And that allowed them to gain enough expertise and capital to then now manufacture something that looks much more polished. And can be mass manufactured. So the White House has taken note. Starting in 2014, there was a White House Maker Fair. Coming up in June, there's another National Maker Fair in Washington, D.C. So this is, I think, for some of the reasons I just outlined, starting to be a national priority to support.
Their dad runs the algorithms department at Pixar, Tony DeRose. Very, very cool family.
Yes. So maybe we can see some similarities here. So from an engineering perspective, there tends to be this confluence of software, electronics, and also some mechanical engineering in many of these projects. And often they're not products per se, but really prototypes, custom one-offs, where making one is the end goal. All right, well, that's certainly nice for all those makers, but what's at stake for us as a larger community, as a nation? Why should we care about supporting the maker movement? And I'd argue there are at least 3 related reasons. There may be more. One is educational. So I'll let you read this quote from Alan Watts. Which just points to the fact that our educational system is very good at equipping us with analytical skills, but maybe not so good at imparting the motivation for what we need those analytical skills for in the end. And so one of the promises of the maker movement in education is that it it serves as a motivator and also as kind of a grounding application of STEM and STEAM skills. And just to, to admit, I have actually seen electrical engineers enter graduate school at UC Berkeley who are completely excellent mathematicians but don't know how to hold a soldering iron. And so this may be a counteracting force. Second argument is made by Eric von Hippel at MIT, which is that often innovations come from lead users rather than out of R&D departments at large corporations, these efforts, because of education, innovation, and just manufacturing knowledge. Now, another question you might ask is, does the maker movement need research? Do they need the help of HCI, computer scientists, mechanical engineers, or are they just fine? Well, I would, of course, argue that there is interesting research to be done and to be contributed here for a number of reasons. First, what you see in the maker movement really inverts how our traditional model of how we think about engineering education. So the traditional engineering education is, welcome to college, take some math, take some physics, maybe some chemistry, then we'll teach you about signals and systems, then an assembly, then come programming languages, operating systems, and all the way at the end, you get to do a nice project that puts it all together. This is turning it upside down. People are motivated to build some project, and then the first iteration gets 80% there, and then something doesn't work. And so that generates a pull, a desire for new knowledge, but it has to be context-specific and just in time. The second interesting part here is that these projects really combine design process, so the exploration of what one should build and the specification what it should be, with fabrication, the actual realization of software, electronics, and hardware components in one iterative cycle. Third, we're seeing just a new digital fabrication tool set making its way from industrial production into end user use, and that brings a whole set of questions with it, namely that amateurs just need different abstractions and affordances from either complete novices who are maybe in an educational program to become experts, or existing experts who have a degree in a specialty. So I think all of these imply a need for new appropriate design tools. So what structures really most or all of the research I'm going to show you today is this research theme for me to try to understand So over the course of the next hour, I will show you projects such as how you can, by simply attaching a single camera to a piece of 3D printed plastic, turn that 3D printed plastic into a working game controller. I'll also show you some brand new work on how to help makers construct circuits and give them interactive debugging help for circuit boards. And I'm also going to show you some new augmented power tools that can give you real-time feedback on the types of tasks you're doing, basically downloading instructions into handheld power tools. But why, right? What's the purpose behind these tools, and who are we trying to help with these? So as the title of the talk indicates, I'm interested in building design tools for the maker movement. So maybe we should just start with a brief summary of what is the maker movement. Well, it's really this bottom-up effort to engage people from all ages and walks of life in learning how the world of products and electronics works and gaining hands-on skills to actively participate in shaping that work. So take this soldering workshop that was in Detroit. Here, there's really a variety of certainly different ages and different experience levels, all trying to be a more active participant in our material world. And of course, ground zero for all of this is the San Mateo Fairground. And Maker Faire is actually this weekend. It's starting today. So if you want to meet your 100,000 closest friends